Well, welcome back. I guess you can see it's time for example number 2. And so let's read it so we can see what it says. This says, a scuba diver is near a shipwreck in salt water. So right there, it seems as though the fluid being displaced is salt water. And so I'll draw a quick sketch of the... First, I need to finish reading it. He's holding a 7-kilogram sunken cannonball made of lead, and it takes up... they give you the volume. Okay, so here's a quick cannonball. This scuba diver, he's holding it, so here's the bottom of the ocean there. Here's maybe the surface. And since he's holding this cannonball, I'm just going to go ahead and show my forces here. He's exerting, maybe we'll call this, I don't know, what do you want to call it? Normal force, support force, I don't know, you can call it whatever you want. I'm going to just call this a FS. Let that be support force. He's supporting the cannonball. We recognize the cannonball has a weight, mg, and this buoyant force. I'll call this FB. So we have 3 vectors here, 3 force vectors. Allow me to select up as positive, and we'll go ahead and finish reading. It says, part A, draw a free body diagram of the cannonball. Okay, well I did skip my givens. Let me just quickly extract the volume, just very quickly before we go on here. 9.05 times 10 to the negative 4 cubic meters of volume. And we see that the density of salt water, along with mass, density of salt water, that's rho SW. That means density of salt water. Just a little higher than fresh water, 1.025 times 10 to the 3rd kilograms per cubic meter. That's salt water. And that's often, you may have heard it's easier to float in salt water. Well, there you are. It's a greater density. So that's going to exert more buoyant force, because you can see density is directly proportional to the buoyant force. The greater the density, the greater the buoyant force. Okay? But anyway, it says in part A, draw a free body diagram. Well, just because we're very habitual about our free body diagrams, we actually did that already. Now we see, draw a free body diagram of the cannonball. Ah, it's done. Now it says in part B, determine the force the diver must exert to hold the cannonball while under the water. So if I can use this as a cannonball. He's holding a cannonball. Gravity is pulling down. He is supporting with his hands, but then the fluid also exerts that upward buoyant force. And so it looks as though we're going to have to apply Newton's second law, because we've got multiple forces here. So I'm going to say let's apply sigma F equals ma. Up is positive, so I will have the support force plus the buoyant force minus mg equals m. But if he's holding it still, what's the acceleration? That's right, you got it, it's 0. There is no acceleration, and so therefore m times 0 goes away. Go ahead and solve. No, it's just algebra now. I mean, this is easy stuff. You want that support force, because look what it says. Determine the force the diver must exert to hold the cannonball. So it seems as though support force equals mg minus the buoyant force. And buoyant force, we remember, is equal to rho of the fluid. Rho, FL, is rho of fluid times volume of object times gravity. Rho Vg is all the buoyant force is. So on this next line, I'll write weight minus rho of fluid, volume of object, gravity. And I could have done that over here. This rho of fresh water, that was the rho of our fluid, FL. This is granite, was the object, OB. So maybe those subscripts will help you. Density of fluid, volume of object, because you don't want to mix those two up. You'll have 2 different materials, fluid and object, don't mix them up. And so this support force, I'm just going to trust you can put the numbers into it for sake of time here, and you should get 59.5 newtons. 59.5 newtons. I'm just going to assume you can put those in. If there's any trouble, just work together, figure that out very quickly.